In this lecture, we'll cover the concept of binding energy. Binding energy for the nucleus. Just go back for the atom. We saw that in case of hydrogen atom, the energy is written as n square. It is z square is 1 for hydrogen atom. And this is how we write the energy in electron volt. So for the electron, which is in the first state where n is equal to 1, this is electron, and this is the nucleus, and you have proton here, and this is one electron. This is n is equal to 1. So this state has energy of minus 13.6, and if you take this electron away to infinity, you have energy 0. So you require 13.6. You have to give 13.6 electron volt of energy to this to make the energy to 0. Initial energy is 13.6 electron volt, plus I give this much of energy to make the energy 0, means I have separated the proton and the electron, because I have taken it far away at infinity. Infinity is only notional, and the energy becomes 0. So 13.6 electron volt was the binding energy of this atom, means to destroy that atom, I need that much of energy. Now we have similar concept of binding energy for the nucleus also. Here we have to understand a very important concept of mass defect, that is delta M is mass defect. If you see that, suppose I am making a nucleus out of so many neutrons, and there are some number of neutrons and some number of protons, and this nucleus is now formed. I have same number of, as I had shown there, suppose whatever, I'm just writing approximately some. This is the nucleus. How many neutron I had here? 1 2 3 4 5 6 7 8 9. Suppose I have 9 neutrons here. 1 2 3 4 5 6 7 8 9, and I will have, suppose, same number of proton. Suppose I had 12 and neutron I had 9. So here also proton I will have 12 and neutron I will have 9. These are when they are not part of the nucleus, and here they are part of the nucleus. The interesting thing is that if you find the mass of proton into number of proton plus mass of neutron into number of neutron, you will find that this mass is greater than the mass of the nucleus, m of the nucleus, which is formed with these many protons and these many neutrons. They are same, but the mass here is less. You had a greater mass. So this decrease in mass, this less mass, is called the mass defect. This is delta M will be equal to this mass, means mass of the individual protons, mass of the individual neutrons minus mass of the nucleus. This is the mass defect, and this multiplied by c square will give you the energy. If I write the masses in terms of atomic mass unit, one atomic mass unit is 931 MeV. I have shown in a different lecture. So if it is an atomic mass unit, I will get the mass defect in terms of the MeV. This energy, because of the mass defect, is the binding energy. Means if I give this much of energy, delta mc square of energy I give to this, only then I can separate the neutrons and protons. So to rupture the nucleus apart, I will have to give this much of energy. The mass defect multiplied by c square is the binding energy. This is the energy by which it has been bound, and I need to give this much of energy to extract all the neutrons and the protons, basically to rupture it. Now there is another way of writing the binding energy. If I show the total binding energy, that makes less significance, but if I show the binding energy per nucleon, or I divide binding energy by the mass number A, I'll get the binding energy per nucleon, means the energy required to take out each nucleon, means each proton and neutron to separate. So higher the binding energy per nucleon, more stable will be the atom, because I'll need more energy per nucleon to destroy that atom. So when the graph is plotted showing the mass number, this is mass number A, and this is binding energy per nucleon is binding energy per mass number, and here somewhere I show 50, here somewhere it is 100, and here it is say 200, something like that. Now when I plot, the graph comes like this, and this is the most stable region because the binding energy here is most, and this is Fe 56. Here you have lithium 6, and somewhere you have B11, you have C11, C12, sorry, you have somewhere here has helium, and you have chlorine, etc., 35 like this, and this is you have uranium 238 somewhere here. You can see the exact picture in the book. I'm just drawing the approximate. So this is the point somewhere in the range of 50s to 60. You have the peak. It is not so flat, it is not so steep, it is slightly flatter. U238 you have there. So this is the region where you have highest binding energy per nucleon, so these are more stable. So naturally there is a tendency for having more stability. So if you can just imagine, at the nucleus will try to move from this position to this position and from here to here, and you can see something very interesting. If it splits here, it needs splitting to reach here, because here the A is high, mass number is high, and here you will need joining of nucleus to reach towards this level. The natural tendency will be to go towards this level of stability to have highest binding energy per nucleon, and this is the fission. This is nuclear fission, and this represent fusion. So the elements on this side are likely to fuse provided the appropriate conditions of temperature, etc., are maintained, and here they are likely to have fission to come towards, to migrate towards the more stability region. So this is briefly about the binding energy per nucleon, and how it is linked with fission and fusion.